Now, the next elementary data structure which we are going to see is the dictionary. Now, dictionary, this is not a new data structure. You have already heard about the binary search trees. Now, what we mean by dictionary is that we mean that there is some element known as a key. So that is why in this course, Design Analysis of Algorithms, we club the binary search trees in terms of dictionaries, because binary search trees work on some keys and dictionary uses keys. There is some uniqueness in the elements. So dictionary in this sense, in this case, is nothing but the binary search trees, which we are going to look at this topic. Now, there is a difference between a binary tree and a binary search tree. Now, the difference is that the binary search tree doesn't Anyway, the difference is that the binary search tree only concentrates about whether there are two nodes or a single node or no node. That means a node in a binary tree may at most have two children. The binary search tree also works on the same concept. That is, it have at most two children. At most two children. Now here, the concept of binary search trees is that a left child is always less than its parent, and right child is always greater than its parent. And one more thing what we have is there are no duplicate elements in binary search trees. Remember that. There are no duplicate elements in binary search trees. The rest of the concepts are same as binary trees, except that in binary search trees, the left child is left child is always less than its parent, and the right child is always greater than its parent. So if you look at this tree, we have, starting with node 20 as the root, what we have is 15 is the left child, 15 is less than 20, and 25 is greater than 20. So at this stage, this is a binary search tree. Now we have to move further, because every node should satisfy that property, except obviously the leaf nodes. So when we look at node 15, node 12 is less than node 15, so it's fine, this property is met. But whereas node 10 is less than 15, which cannot be. As well as in this case of node 25 and node 22, 22 is the right child of node 25. So this does not satisfy the property of binary search tree. So this tree is, though it's a binary tree, but it's not a binary search tree. Now let us look at another example. Let us look at this example. We have node 30 as the root. Node 5 is less than node 30, so this left side property is satisfied. Node 40 is greater than node 30, so right side property is satisfied. Now coming to node 5, node 2 is left child and it is less than, so this property is satisfied. So every node is satisfied that property of a binary search tree. So this tree we can call it as a binary search tree. Now what about this tree? Is it a binary search tree? Node 60 we have, there is no left subtree or left child for node 60, but whereas node 70 is the right child, so node 70 is greater than node 60, so it's this property of a binary search tree is satisfied at this level. And for node 70, node 65 is less than node 70, so left's property is satisfied, and node 80 is greater than node 70, so even the right property is satisfied. So this is also a binary search tree. Now, the basic idea or the purpose of binary search tree is that the keys or the elements. Keys, we are calling elements as keys because they are unique. The keys or the elements are in such an order that the left child is always less than the root, or it's sorry, not root, its parent, and right child is greater than its parent. That is why we are calling, they are unique elements, we are calling it as keys, and that is the property of the binary search tree. Then the purpose, we call them as search because it is very easy to search the nodes or the keys in the binary search tree because of its property. So that is why the searching, what we say, we can efficiently search any element, whether it's present in the tree or not. Now, there are two ways of searching it. One is to use recursive. The other one is to use iterative search. Iterative procedures. Now, what you are looking at what you are looking at this stage at this algorithm is a recursive algorithm to search an element. Now, let us try to search element 10. So what happens is, this T is the entire tree what we pass to this algorithm, and X is the element we are trying to search, that is the key. In this case, let us assume that it is element 10. Let us say X is 10. That's the element we are trying to search. Now, it starts from T. Obviously, T is representing the root or the entire tree. So, what that means is T represents the root, or it has the address of the root. Then, we first need to check whether is the tree empty. That means if T is equal to 0, that means there are no elements, and then we just return 0. Now this condition, T equal to 0, is at the first instance used to say that whether there is any elements in the tree or not. And the other thing is, this condition is known as the base condition for our recursive calls. Now this base condition will be evaluated each time a recursive call is made. So initially, T is not null, it's pointing to node 20. Now, the next statement what we check, obviously this is not true, T is not 0. So we come to the else if. In the else if, X, which is 10, is equal to T of data, that is equal to 20. Data is 20, that is data stored inside the node. Now even this is not true. So if we look at the next else if statement, the condition, X is less than T of data, that is 10 is less than 20. Obviously 10 is less than 20, so this condition is true. So therefore, we make a recursive call, that is, we are calling this search algorithm again, passing the root's left child and obviously the element 10 which we are trying to search. So T arrow L child is the left child. So T now will be pointing to this node. T will now be pointing to this node. Just a second. Anyway, sorry for the disturbance. We were at this stage. So T of left child is passed. So now this T over here is nothing but referring to node 15, which is the left child of node 20. Then again the recursive function algorithm is called, and now T is not null, which is a node there. Then X equal to T of data, X is 10, T of data is 15 now, so 10 equal to 15 is also false. Now we have else if. where x less than t of data, so 10 less than 15. Oh, I'm sorry. This tree itself is wrong. Sorry. Just let me change this. How do I go? Okay. Now, let's say this is not 10. Let's say this as 18. This tree itself is wrong. Sorry. Where is it? This also, let me make it as 18. And this one as 28. This is 18, this is as 28. This is 18, this has 28. Okay, let us continue. Sorry, the tree itself was wrong. I mean, the basic purpose 15 less than 10, I mean, it was not right. Anyway, let us try to search for element 10 itself. So here we will be passing element 10, and then t is starting from the root node. This is t. T is not null, not 0. So if statement executes, x equal to t arrow data, which is x is 10 equal to 20 is false. So we have else if part. In the else if part, we check whether x, which is 10, less than t of data, which is 20, is true. So we recursively call the search algorithm, that is the same algorithm, passing t of left child. So t will now be representing the left child of node 20. And obviously x is same, that is 10, which is the key we are trying to search. So now when this is recursively called, what actually happens is the algorithm will again work or now work with the left child, that is t is now node 15. Then the first statement t equal to 0 is checked, which is false. So we have else part where x equal to t of data is 15. So x equal to 15 is false. Then we have the else if statement where we have x, that is 10, less than t of data is 15. Yes, 10 is less than 15. So we again recursively call the search algorithm, again passing the left child, because it is the key is what we are trying to search is less than the present in the parent. So we pass the address of the left child, or we pass the left child. So now t will be pointing to this node, that is node 12. Then when it is pointing to node 12, again what happens is t is not null, it's checked, that's false. There is a node which is 12. 10 equal to 12 is false again. Then we have the else if statement. 10 less than t data is 12. So 10 less than 12 is true. So again recursively we are calling the search algorithm, passing its left child. So t will now be pointing to somewhere over here as which is the left child of node 12. Again the recursive algorithm is called. Now when we have the statement t equal to 0, that means there is no node here. So t is actually pointing to null or 0. When there is no node, t is pointing to null or 0, we return 0, which means that the key, that is 10, which we are trying to search, is not present in this binary search tree. Now similarly, if we try to search for element, let's say 18, element 18 recursively starts from t, and then we don't at this stage we check if 18 is equal to 20. It's not. So we move to the left child. We check here if 15 is if 18 is less than 15, which is false. So we move to this else part where we it's obviously if it's false, what we do is we recursively call the search algorithm passing the right child. So T will now be pointing to this node, which is 18. Then it's recursive. The algorithm is recursively called. So once it is recursively called, at this stage, once it is recursively called, T will be pointing to 18 and we are trying to search 18. So this statement, T equal to 0, it's false because T is pointing to some node. Then X, which is 18, in this case our search key, equal to T arrow data, which is 18, is true. So we return the node. That is, we return tree saying that the element is found at that address or at that node. So this is how a binary search can be performed, or binary search tree can perform searching. Looking at the left child, first looking at the root, if it's present or not, then looking at the left subtree or searching in the left subtree or searching in the right subtree depending upon the condition, and then finally at the leaf node level. At the last level, a node may be found or may not be found. That is, it may be accessing or it may be referring to a null node. So that's how the binary search operation in binary search tree works, and this is what is the recursive process. Now same way we have the iterative process. In the iterative process, we try to make use of a variable found known as false, and T equal to tree, that is this whole tree. We are saying that it's represented using the root node, and then we check while T not null, like we checked in while T equal to 0, we return 0. So if T equal to 0, we return 0. Here we are making use of a while loop because it's a recursive call. And if T is not null and not found, suppose if it is found, then there is no need to repeat this while loop. So we check if not found, then we first check whether X is equal to the data, that is the key is equal to the data which is present in the node. If this is true, then we say found true, that is we found the element. Else if we check, the conditions are same. If you observe the recursive algorithm and this algorithm, conditions are same. If X is less than the data present in the node, then we move T to the left child. T is moved to the left child. Else, that means the key is greater than the element in the node, so we move T to the right subtree or the right child. So this while loop will continue until we find the element or T becomes null. So when T becomes null, the while loop terminates, and we say if it is not found, we return 0, else we return T. Now this part obviously is not needed actually, but anyway, as per the formal algorithm, we have to have this part because if it is found, then we have to return its the address of the node or that node itself. So here we are just saying that if it's found be true, and once this becomes true, then while we come out of the while loop, and if it's not found, we are returning 0. If it's found, we are returning T, that is the node itself. So this way, the binary search tree performs the search operation using iterative or the recursive methods or approaches. Now let us look at the inserting an element to binary search tree. This is one of the most, important operation that has to be performed on binary search trees. Now, we had looked at the search operation before inserting or before creating a tree itself. That was because to insert a node, we actually perform the search operation and search for the place where that node can be inserted. So that is the reason we saw the search operation before actually inserting the nodes or creating the tree itself for the binary search, creating the binary search tree itself. Now in this case, if you look at this tree, it's already, have some elements or keys, and this satisfies the property, or this is the binary search tree itself. Now let us look at inserting an element. Let's say element 80, element 80 in the binary search tree. Now the concept of inserting is that we start from the root node. Now if there are no elements in the tree, root node will be null. So if there are no elements and we are trying to insert an element, then we simply make that element as the root node of the tree. If there are no elements and we are trying to insert an element, there is no need to search because there are no elements. So we make that element as the root node itself. Suppose if there are some elements and we are trying to insert element 80. So what we do is we start from the root node, that is, in this case it's node 30. Check whether the element which we are inserting, that is element 80, is equal to that node or not. If it is equal, that means we cannot insert that node. Why? Because binary search trees has a property that they are unique elements in the binary tree. No duplicates, unique elements. So we check if it is equal to that element. If it is equal, then we say the element cannot be inserted. If it is less, then we traverse the the left subtree, and if it is greater, we traverse the right subtree. So in this case, we are inserting element 80 or element 80. It's greater than. So we move this t to its left child. Then, we move t to not left child, right side, because it's greater than right child. Then again we check the element which we are inserting, that is 80, with element in the node, that is element 40. Is it greater? Is it equal to? No. Is it less than? No. It is greater than. So that means this t should move to the next node. But when it moves to the next node, what happens is it will be pointing to none. So what we do is, initially we start with t, let's say p, let's say t itself, okay. We will have another variable as pt, which will also be pointing to the root node. Then we check whether the key 80 is equal to or less than or greater than. In this case, it is greater than. If it is less than, then we will move t to the left child. But it is greater than, so we are moving t to the right child. Now, we are comparing again with 40, so pt remains as it is at this place itself. Now, when we compare this 40, equal to, less than or greater than. If it's less than, we will move the element 80 which we are inserting is less than, we will move t to the left subtree as a left child, left node. Or if it is greater than, we will move to the right. Now it is greater than. So what we do is, we move t to the right subtree, right child, and we move pt. We were using two variables. 2 pointers, pt. We move pt to t, or we make t as pt and then move t to the right child. So pt will be pointing to parent, t will be pointing to the child, though there is no child over here. Now again we compare, but there is no element here. So that means we found the position where 80 has to be inserted. So where should it be inserted? It should be inserted as a child of node PT. The while loop terminates here because the t has reached to null. So because we will be doing using a while loop, so we'll reach t when t reaches null, it stops, and pt will be pointing to the node or the place where the node 80 has to be inserted as the left or the right child. Then once we find this element outside the loop, because loop will be used to traverse to the last level of the tree, outside the loop, what we do is we will try to check if 80 is less than 40. If it is less, it will be the left child. If it is greater than 40, the element we are trying to insert, that is 80, then it will be the right child. So in this case, it's the right child. So element 80 will be inserted as the right child of this node. So element 80, which we are trying to insert it, is the inserted the right child of node 40. Similarly, if element 35 is there, suppose we are trying to insert 35, then where will it get inserted? 35 is greater than 30, so obviously we may need to move to the right side or right subtree. Then we check again with 40. 35 is less than 40, so we have to move to the left child. Then we know the parent, pt will be pointing to 40. Then again 35, that is the element we are trying to insert, will be inserted at this place. So this is how insertion happens in the binary search trees. Now let us just briefly look at the insert algorithm. Now here if you see insert, this insert algorithm takes the key that has to be inserted. In this case, let's say we are trying to insert 22. Let's take another example, 22. Found is false, initialized to false, p is initialized to the tree. So p will be pointing here. Then what we have is p is not null, found is not found. We take use of q. I took pt. Here in this algorithm, a formal algorithm is using q as the variable to refer to the parent. Then we will check if it is equal to, then we say found. That is, we cannot insert that element, will be a duplicate. Else if it's less than, we move to the left subtree. If it is else, we move to the right subtree. So in this case, 22 is greater than 20. So p, look at here, p equal to p arrow r. So only p is moving at this top point. P is moving. Then we check while p is not null. Then q is assigned p. So now q will not be pointing here. Q will be coming to this node. So it will be pointing to this node, that is 25. Then we say is equal to, no. Less than, yes. So p will move to right child. So p will be moving here. And p will be pointing to the left child of node 25. P will be pointing to the left child of node 25. And again the loop executes. P null, yes, p is null because there is no left child for node 25. P is null. So remember, q has just moved till its parent. So q will be pointing to the parent of p. Obviously there is no node p, it's null, but q will be pointing to the place where the node 22 which we are trying to insert, or the element 22 which we are trying to insert, will be placed. So then we check if it is found, because if found is true, that means we cannot insert, though that is not the case here. So we create a new node, and a new node is created. Left child of that node and right child of that node is null. X is assigned, which is the value 22. Then we check if tree is not null, because if tree is null, that means obviously there are no elements in the tree, and this tree becomes the root node, that is else part will be executed, which p itself, this while loop will not execute if there are no elements, because p initially will be false. This loop will not execute. We have not found. This will not execute. Else we have a tree. We make that P itself as the node. The root node for that tree. So tree will be assigned P itself. That is the node itself. If it's null, so this new node will be there. So, but in this case, it's not that we are having elements. So the tree is not null. So we check if it is less than. If it is less than, we make Q arrow left child. This is Q. This node 25 is Q. Q arrow's left child as P. This node is P. So this P, we make this as P. Else we make at the right one. So this is how insert algorithm will be functioning or will be running. Then let us look at the deletion. We have seen insertion. Let us look at deletion. Now inserting is easy. It takes the search, make use of the search procedure, and then insert the element to the left or the right child. In deletion, there is little complexity. Deletion is not that easy as insertion. In deletion, actually we have three cases. We can delete the leaf node. That's very easy. It's the easiest case. Deleting the leaf node. Now when leaf node is deleted, when the leaf node is deleted, since it's there is no children because it's a leaf node, its parent's left or right child will be made as null. So for example, if we have this node 2, if we are trying to delete this node 2, there is no problem because there are no nodes to left or right. Just make the left child of node 5 as null. It's deleted. The second case is that a node may have a left subtree or a right subtree. For example, in this case itself, node 5, if you take it, it has left subtree as well as it has only left subtree. If you take node 40, it doesn't have a left subtree, but it has a right subtree. So the second case is trying to delete a node which has left subtree or a right subtree. This is a complicated case. Now, when, for example, let's say node 2 is the left child of node 5, and we are trying to delete node 5. When we are trying to delete node 5, we simply cannot delete this node because if we delete this node, we will lose the reference to the left subtree of this node 30. So what we have to do is, we have to make, since it's a left child, we have to make the left child of node 30 as node 2. Then we will be able to delete node 5. Now why we have to make node 2 as the left child of node 30? Because node 5 which we are deleting, the node which we are deleting is the left child. So directly we can link the children, the child of this node to node 30. Then delete this node 5. In the same way here also, if I have to delete node 40, then node 40 is the right child of node 30. So nodes 40's children, whether it is, it may have any let's say any other child, let's say 50 or let's say 100, doesn't matter. I simply have to make the right child of node 30 as node 80. The rest of the other things will be as it is, will not affect. So in the second case, when there's only one child when there is only one left subtree or the right subtree, then we have to make its parents left or right subtree linked to its child. So that way the second case is handled. Now with regard to the third case, which is most complex. The third case is most complex. That is, you can see here node 80, node 30 in this case has got both left and the right subtree. Both left and the right subtree. So first case was deleting the leaf nodes where there is no children to the node which we are deleting. Second case was deleting a node where we have a left child or the right child or left subtree or the right subtree. And the third case is deleting a node which has both left as well as right subtree or both left as well as right child. And this is the most complicated case or most complicated scenario.
Now in deletion, it's not that easy when we use deletion. Deletion has three possibilities. Now it can be a leaf node that we are trying to delete. That is what we talked in the last class. And for example, in this case, 15 is the leaf node, 45 is the leaf node, 56 is the leaf node, 70 is the leaf node, 95 is the leaf node. So deleting the leaf node is very simple. Now what we need to do it is we need to just make the, for example, if we are trying to delete 15, 15 is the right child of node 12. So we simply have to make the reference of the right child as null in node 12. So 15 gets deleted. Now there is another possibility that a node which we are trying to delete will have one child left or right or one subtree left or right. Now for example, if you take node 12, if you are trying to delete node 12, node 12 has a right child. We call this as right subtree. And then if we take node 60, node 60 has got a left child at the root there of the left subtree. So it's the left subtree which node 60 has got. So the second possibility is that deleting a node with one subtree, right or left, or one child right or left. Then the third possibility is to delete a node which has two subtrees, left as well as right. And in this case, for example, if you see node 52 is there, it has both left and the right child or left and right subtrees. Node 90 is there, it has both left and right subtrees. Node 65 is there. This entire thing with 60 as the root is the left subtree, and this entire thing is the right subtree. As well as node 40, which is a root. Even root has, in this case, has got two subtrees. That is, this from node 12, 15 is one subtree, that is the left subtree, and from 65 till whatever we have as part of its children is the right subtree. So there are three possibilities or three scenarios. Now, deleting, as I told you, deleting a leaf node is very easy. Let us try to look at deleting once a node which has one subtree. Let us consider the case of 12. In 12, node 12 has only one subtree, that is the right subtree with node 15. So what we have to do is, whether it may have other children of node 15 doesn't matter. But what we have to do is, the node 12 is what we need to do is node 12 we are deleting. Node 15 is the right subtree, and node 12 is the left subtree of node 40, its parent, left subtree of its parent. So for node 15, the link is, from node 12, node 15's link is deleted, and there is a link from node 40, that is node 15 is made as the left child of node 40. So this is how a node with one subtree is deleted. Let us look at another scenario. Node 60 is there. Node 60 has got one subtree, and there are so many nodes. There are three nodes in the subtree. So in this case, what happens is node 60 is left of 65, and 52 is also left of 60. So we have to make a link, or we have to make node 52 as the left child of node 65. So we first make remove node, then we make the left child of node 65 as node 52, and the entire tree structure remains the same. The rest of the entire tree structure remains the same. So this is how we delete nodes with one subtree, left or right. Now, the most difficult part or scenario is deleting a node with two subtrees, that is left and right subtrees. Let us consider this node 90. Node 90 has got node 70 and node 95. Now here, if you observe, node 70 and 95, they are not, they don't have their children. They are the leaf nodes. So this is one scenario. And this is pretty much straightforward, that when we are deleting a node, for example, node 90, any of these children, two children, should be made as the node itself, and rest of the child remains the same. For example, let us consider 70. So when we are deleting node 90, we can either make 70 as node 90 and delete node 70. So tree structure remains the same. The property of binary search tree is satisfied. Or we can make, for node 90, when we are deleting node 90, we can make the right child as the node and delete the right child. So this is one possibility. This is pretty straightforward because the left and the right child do not have their children. But if you observe, what we try to do it is, how we generalize this is that when a node with two subtrees, left and right, both left and right is deleted, we will select the largest node from the left subtree. Remember, largest node from left subtree, and replace with the root. Not root. Replace with the node which we are deleting, and then the next node of that tree, we will make it as the left child. We will look at that scenario. Or in left subtree, we are selecting the largest node. If we consider the right scenario, if we are considering right, replacing the right node, then you have to select the smallest node from the right subtree. So that is why here in this case, if I consider replacing with the left part or left subtree, then there is only one node. So this is the this is the largest node itself. So we are replacing it. Or when we consider the right subtree, this is the only node. So it is the smallest node itself, and we are trying to replace it and delete that node. Now let us try to take another scenario. Suppose if we are trying to delete node 65. It has both subtrees. Left subtree starting with the node 60, that's the root. Right subtree with node 90, that's the root of the right subtree. Now, when we are deleting this, node 65, if we consider the right, if we are considering the left subtree to replace that node, then node 60 is the maximum element in the left subtree. That element will get replaced with node 65, that is the node we are deleting. So we replace node 65 with node 60 because we are considering left subtree, so it's the largest element from the left subtree. Then we make the child of the node as the left subtree. So this satisfies the criteria. But suppose if we are considering the right subtree, in the right subtree we have to select the smallest element and replace with the node. So node 70 is the smallest element. We are replacing that with the node which we are deleting. So that gets replaced, and simply node 70 gets deleted. The rest of the links are same, and the structure of the tree remains the same. So this is how deletion in binary search trees is performed. there are three possibilities. That is deleting a leaf node, or deleting a node with left or right subtree, and deleting a node with both left and the right subtrees. Deleting the node, leaf node is very easy. Just simply make the left or the right child as null. The parent of the make the left and the right child in the parent node as null. That deletes the leaf node. If you are having two nodes, if you are deleting a node with one subtree left or right, then delete that node, but make the parent, whether it is left or right, as the link to the child of the left, or the child or the root of the left or the right subtree. Then if you have two subtrees, left as well as right, then you can select either the left subtree and choose the largest element or node and replace with the node which we are deleting, and subsequently create the links. If we considering the right subtree, then choose the lowest or the smallest element and replace with the node which we are deleting, and subsequently attach the links. So this is how, or this was the basics of the binary search trees or dictionaries.